Okay, this is the pre-class lecture for Wednesday, September 19th. So we've so far talked about non-cyclic alkanes, the branched and straight-chained alkanes. And so now we need to talk about cyclic alkanes. And in general chemistry, you very rarely wrote a cyclic Lewis dot structure because for the most part, if you did, it was wrong. So what in organic, though, cyclic compounds are pretty common. And so here are some examples of cycloalkane rings that are made up of 3 carbons, 4 carbons, 5 carbons, and 6 carbons. We're going to spend most of the time talking about 6 carbon rings, both in this lecture and the one for Friday. So first, these are called cycloalkanes. So the name of this molecule with a 3 carbon chain would simply be cyclopropane. We have cyclobutane, cyclopentane, and finally cyclohexane. So what we're going to do is we're going to talk about, first of all, how to name them, some of the structural features of the 3 versus the 6 carbon ring, and then we'll spend Friday's lecture talking about the conformations of cyclohexane molecules. We'll get into a little bit of that today. So let's start with IUPAC names for rules for naming cycloalkanes. So what you do is you begin numbering the cycloalkane ring at the carbon that's attached to the substituent. Now before I start, I should say that what we're going to do is we're going to treat the cycloalkane ring as the parent chain. Okay, so that's an important thing that we have to realize is that the cycloalkane ring is going to be the parent chain for the molecule. And so we already have the parent ring predefined. Now we have to do is figure out a numbering scheme. And so what it says to do is begin numbering the cycloalkane ring at a carbon that's attached to a substituent. And the rules for numbering are a little bit different than they are for acyclic or non-cyclic alkanes in that you're going to number the ring clockwise or counterclockwise. And the idea here is to get the lowest sum of the substituent numbers. Now, in order to get the lowest sum, you need to start at a substituent. You have no choice in that matter. And then if you have 2 or more possible numbering schemes, you're going to start numbering at the substituent that's alphabetized first. And if you have to break ties, we're going to break it on the alphabetization. And then we name, number, and alphabetize the substituents as before. And then we're going to have our numbers, our substituents, and then the parent name will be cyclopropane or hexane or whatever the cycloalkane ring is. So let's look at an example here. First of all, this is going to be a cyclohexane. And we have to number this ring to get the lowest total sum of the substituent numbers. And there's 2 possible ways to do that. I could start here and go 1, 2, 3, 4, and that would give me a total sum of 7 for the red numbering scheme. Or change colors, and we could have a blue numbering scheme that would go, maybe I want to do this, 1, 2, 3, 4, 5. Now look, that blue numbering scheme has a grand total sum of substituent numbers of 8, so I'm not going to use the blue numbering scheme. I'm not going to start numbering down here at 1, 2, 3, and 4, because that would give me 8 as well. So I put those in triangles to differentiate them. So in this case, we actually don't have more than one numbering scheme. The only one numbering scheme gives us the lowest total sum of substituent numbers, and that's the red one. So that's the numbering scheme that I'm going to use. Okay, we'll do a few more problems, but that's the idea. The idea is get the numbering scheme that has the lowest total sum of the substituent numbers. So in this case, now I'm going to go ahead and name my groups. I have a 1-methyl. I have a 2 either isopropyl, or I could call that again a 1-methyl ethyl, and a 4-ethyl group. And so from here on out, it's just writing the name like we had done before. If I write this with an isopropyl, I'm going to have 4-ethyl, 2 isopropyl, 1-methyl, cyclohexane. Okay. If I write this with a 1-methyl ethyl, I'm going to have 4-ethyl, 1-methyl, because remember methyl comes before methyl ethyl, and then 2 1-methyl ethyl cyclohexane. Okay. So the trickiest part of naming cycloalkanes is simply finding the numbering scheme. Again, the rules here are the lowest sum of substituent numbers. Okay, here's another example. Can you find the numbering scheme that would give you the lowest sum of substituent numbers? If you need to, shut the tape off for a minute. If you shut the, whatever this is, video, and see, can you number the substituents to give the lowest total sum? Okay. If I was to do this, I would number here, number 1, 2, 3, and 4. That would give me a total of 7. And there's another way to number this, which is to start here and go 1, 2, 3, and 4, and that blue would then give a numbering scheme of 7 as well. Now notice I had to actually start numbering at the carbon that had the 2 substituents, because there's no other way possible to get the lowest total sum unless you start at the carbon with the 2 substituents. 1 plus 1 is always going to be better than any other combination of numbers. So in this case, how do I break that tie? Well, I'm going to break the tie based on alphabetization. Bromine is going to come before chlorine alphabetically, and so therefore I want the bromine to have the number 3 versus chlorine having number 4. And so in this case, I'm going to use the red scheme, and I'm going to have a 1,1-dimethyl, 3 bromo, and 4 chloro. And so now writing the name, it's going to be 3 bromo, 4 chloro, 1,1-dimethyl, cyclo, and in this case it's a 5-carbon chain, so it's going to be a cyclopentate. Okay. So when you have 2 substituents, you pretty much have to start at numbering at that carbon that has the 2 substituents attached. Okay, here's 2 more. Can you write the names of these 2 molecules? If you think you have it, then stop the video and go ahead and write out the 2 names, and we'll see if you're right. Okay, for the molecule on the left, I can either number this 1, 2, 3, or I could number this 1, 2, 3. That's going to give me the lowest sum of substituent numbers. The choice here is to start numbering at the methyl group or start numbering at the chloro group. What do you think we'll do? We'll start numbering at the chloro group. So I'm going to use that numbering scheme. So this is going to be 2 bromo, 1 chloro, 3 methyl, cyclohexane. How about the one on the right? Well, in this case, I again have 2 numbering schemes. I could go 1, 2, 3, and 4, or I could go 1, 2, 3, and 4. Now in this case, I could start with a methyl versus a methyl, so they're tied. So now I'm going to go one more substituent in and see ethyl versus bromo. In this case, the bromo wins, and so I'm going to number counterclockwise. And this is going to be a 2 bromo, 3 ethyl, 1,4 dimethyl cyclohexane. Okay. So we have to first find the numbering scheme that gives the lowest sum of substituent numbers, and then if we have to break ties, we start with where we start the chain, or where we start numbering. The first alphabetized group will get that. We'll win priority there. And if not, we just keep going until we find a point of difference like we did in the right-hand molecule here. Okay. Last one, what would this one be called? That's the numbering scheme I would use because it gives a total of 7. And my choice is between starting at methyl or ethyl. Ethyl wins. And so this would be 1,4 diethyl, 2 methyl cyclopentane. Okay. Now, we know how to write the names of complex substituents. When you have a monosubstituted cycloalkane ring, you have actually 2 options. You could name this, in other words, in this case, I could name this alkyl group according to its IUPAC name and then call it cyclohexane. Now, can you do that? What would be the IUPAC name of this alkyl group? Take a second and write it down. Okay, hopefully you wrote it down. And so I would start numbering here, 2, 3, 4, 5. So I would call this a 1 ethyl, 2 methyl pentyl cyclohexane. This is one possible name for this. You may say, do you have to put a 1 in front of it? Well, if there's only one group, by definition, that goes at carbon 1. So this 1 here, that's optional. I'll leave it up to you whether you want to put it in or not. Usually we don't. So one name of this molecule would be to call it 1-ethyl-2-methyl-pentyl cyclohexane. Now sometimes what we do when we have just a monosubstituted ring is that we name the ring as a substituent of the longest chain of the alkane. For instance, if I want to treat a cyclohexane ring as a substituent, I'm going to call this a cyclohexyl group. And I would say that in this case, my longest continuous carbon chain, I'm going to look at this as an alkane, And so another possible name I could use would be, I could call this 3-cyclohexyl 4-methyl heptane. And so that's sometimes done when you have a monosubstituted cycloalkane. And so you just simply, this is a cyclohexane that's now a substituent, so we change it to cyclohexyl. What do we alphabetize on? Since this is all one word, we alphabetize on the C. So another possible name of this molecule would be 3-cyclohexyl 4-methyl heptane. Okay, so sometimes we'll name the cycloalkane ring as a substituent, but we now know how to name the complex substituent, so we could do it either way. Again, you're only going to do this for a monosubstituted cyclohexyl group, because otherwise it gets too difficult to tell where the cyclohexyl, if the cyclohexyl has another group on it, then it just becomes very confusing. So if it's more than monosubstituted, we name the alkane based on the parent name being the cycloalkane. Okay, and that's pretty much what this slide says. Okay, cycloalkanes though are they're kind of unique in the fact that I can now have stereoisomers for cycloalkanes. And so it's possible to draw stereoisomers for 1,2-dialkyl cyclobutanes. So in other words, I've got two alkyl groups at 1,2. Actually, this should say 1,3. Whenever I have a disubstituted ring, I can have stereoisomers. So let's remember, what are stereoisomers? Stereoisomers are the same structural isomer, but they differ in three-dimensional shape. And our examples from before, remember, were when we had a carbon-carbon double bond, we could have our geometric or cis-trans isomers for the double bond. Well, remember the technical difference between these geometric isomers or these cis-trans isomers versus conformers was that cis-trans isomers can't be interconverted. You've got to break the pi bond in order to convert cis to trans. For conformers, we could convert those by simply rotating around a single bond. Well, the types of stereoisomers that we can get for cycloalkanes are these cis-trans geometric isomers. And so let's say I have a cyclobutane with two different alkyl groups attached to it. Now, this is my opportunity to introduce the R terminology. First, if you look on the periodic table, there is no element R. R just is an abbreviation for any alkyl group. That's traditionally what's been used in organic chemistry. So R could be methyl, ethyl, propyl, butyl, 100 carbon chain. R just means there's some alkyl group attached. So if I have a dialkyl cyclobutane, it turns out that those alkyl groups could either be aligned on the same side of the ring or on opposite sides of the ring. And so we use our cis-trans terminology to say that if the two alkyl groups are on the same side of the ring, we call them cis. If they're on opposite sides, we call them trans. Okay, we're going to call this the cis cycloalkane or the trans cycloalkane. Now, we can't interconvert cis and trans. So these are our geometric isomers. Because in order for me to convert cis to trans, I would have to break the single bond and then rotate around the carbon. Well, that's not going to happen at room temperature. So cis-trans isomers for cycloalkanes are exactly like they were for the carbon-carbon double bonds. They're distinctly different and they cannot be interconverted. Okay? So we can't interconvert cis to trans without breaking a bond. Okay, and that just can't occur at room temperature. So there's a couple ways we can draw out the cis and trans isomers to show the stereochemistry. The first that we could do, and I'm going to change this and I'm going to do this with a cyclohexane ring, is often in biology you'll see cyclohexane rings actually with an oxygen here. You'll see the cyclo, in this case this six-membered ring, drawn like this, where you have R groups and you'll represent the R groups, let's say, on opposite sides. So there's the trans, and then, you know, maybe here is the cis. Now these are actually called Hallworth projections, and if you remember seeing these in biology, you didn't see R groups, you saw OH groups, because this is how you represent sugars, things like glucose and maltose and all of the six-membered ring, dextrose, the six-membered ring, sugars. But this actually isn't all that helpful. Sometimes we use it in organic chemistry, but not very often. We'll talk about how to represent the six-membered ring here in a couple of minutes. But the other way to represent cis and trans is to use our tetrahedral representation. So let's say for a six-membered ring, I have two alkyl groups. I might say, hey, I'll just write the cis this way. Or I'll write the cis that way. So both of these are the cis stereoisomers. Okay, the tetrahedral representation, it's as if I'm up here looking down on the ring. And so if both groups are pointed towards me, it's cis. If they're pointed away from me, it's cis. Now the important thing to represent, to realize here is that where's the hydrogen at? Well, if I've got two bonds in the plane of the board and one pointing towards me, that means in this case these two hydrogens are actually away from me on dashed lines. And down here the hydrogens are on bold wedges pointing towards me because I need two bonds in the plane, a bold and a dashed wedge. So how would I write the trans isomers? I could write them like this, or I could write them like that. So we'll represent cis and trans when we're doing naming by showing the bold and the dashed wedges. So what we're going to build up to here in a minute is that if you're given the cis or the trans stereoisomer, you need to make sure that you include that in the name of your cycloalkane. But in order for you to include that in the name, you need to be shown explicitly what you're looking at. And so you need to see the bold and the dashed wedges to tell whether the groups are above or below the plane of the ring. If you just see straight lines with no bold and dashed wedges, then I'm not showing you the stereochemistry of the cycloalkane. Okay? So basically that's what I would do here with the trans. I already wrote cis and trans earlier. So what would be the name of this molecule? Now I see bold and dashed wedges here, so I'm asking you, is this the cis or the trans? And so naming this, I would start numbering here, 1, 2, 3. So this would be a 1-ethyl, 3-methyl, cyclopentane. And because I've specifically given you the trans with the bold and the dashed, we have to include that in the name. So this would be called trans 1-ethyl 3-methyl cyclopentane. Okay. So 2 bolds are cis, 2 dashes are cis, mixture is trans. Okay, and we have to include that in the name if I give you that, if I give you bold and dashed wedges. Okay. Now to complicate things a little bit, you can only use cis or trans in the name when you have 2 groups on the ring. Okay. We can't use cis or trans in the name when you have more than 1 or more than 2 groups attached to the ring. And here's a perfect example. If I called this cis, the first question that I would ask would be, well, what groups am I talking about being cis? Or if I said this was the trans and I put that in the IUPAC name, since I have 3 groups, it's not clear what 2 groups I'm talking about being trans. Now, that doesn't mean that I couldn't say that these 2 methyl groups are cis or that this methyl and ethyl group are trans. It just means that when you have more than 2 groups attached to the ring, you cannot name this with the cis or the trans before the name. You may ask, how would I name this? Wait a few weeks and we'll get there. Okay. So we can use cis or trans if we're pointing out 2 groups, but we can only use it in the IUPAC name if we have just 2 groups on the ring. And again, they have to be shown with the bold and the dashed wedges. Okay, last topic for this pre-class lecture is the idea of ring stability and sometimes what is called ring strain. And your book has the quantitative measures of this ring strain. I'm going to go through it qualitatively. What we find is, we find that a cyclopropane ring is unstable, or it's the least stable. I won't say unstable, but it's the least stable of the cycloalkane rings. Cyclobutane is next, and cyclopentane and cyclohexane. Cyclohexane is actually the most stable of these rings. And so cyclopropane has what's called ring strain. Cyclobutane has a little bit of ring strain. And so how do we determine, well, how do we know that cyclopropane and rationalize that it's the least stable, but yet cyclohexane is the most stable? Well, let's look at what a cyclopropane ring really looks like. It's a triangle. It's a triangle with all of the sides the same. And therefore, we'd have a 60-degree bond angle between the carbons. Now, we know that this carbon is sp3 hybridized and therefore would have a 109-degree bond angle in its orbital picture. So if I look at this picture, you can see that these bond orbitals, the sp3 hybrid orbitals, are at 109.5. Well, how do you make a 60-degree angle out of a 109.5 angle? The thing is, you don't. What happens is, instead of the carbon-carbon bonds being formed by direct head-to-head overlap, because it's a 60-degree bond angle that doesn't match up with a 109.5-degree bond angle, instead we have them kind of like skew here. And so they don't quite overlap perfectly head-to-head. And so what that does is that makes a weaker carbon-carbon bond. Okay, the strongest carbon-carbon bond would be if those orbitals overlapped perfectly straight on head to head. When they overlap at a skew, it's going to make a weaker carbon-carbon bond. But there's nothing I can do about that because I'm forming a 60-degree triangle. So how do I know that that's the case? Well, if I take cyclopropane and I add hydrogen to it, I could actually break the ring open and form propane. Cyclobutane, though, doesn't have that much strain in it, and so when you add hydrogen to it, you get no reaction. So it turns out that cyclopropane is, in this case, what we would call more reactive, right? Because it's reacting with hydrogen, and cyclobutane is not. And in chemistry, we have the reactivity stability issue. The more reactive a molecule, the less stable it is. The more stable the molecule, the less reactive it is. You can probably apply that to people too, but that's a topic for another class, not organic chemistry. So cyclopropane is less stable and more reactive. Okay, so that's evidence of it's what we call ring strain. Now, when you go to a 5-membered ring, you would predict that the cyclopentane would be probably the most stable of all because you've got a 105.5 degree bond angle, and that 105 degree bond angle is pretty close to the 109.5. Cyclobutane, you might say, but that's 90 degrees. That's still not matching up with 109, but it's getting closer. Well, it turns out that these are stable. These are more stable than cyclopropane because they can do what's called puckering. Okay, and I said that word very carefully. So this is a cyclobutane, and notice that the cyclobutane does not have all 4 carbons in the plane. It puckers in order to relieve some of that angle strain so that it still has to kind of be 90 degrees, but it can kind of relieve that a little bit in the molecule by puckering. Cyclopentane has an even easier time because with 5 carbons, it can actually bring one of them out of the plane, and so it sometimes forms what we call an envelope conformation. And so cyclopropane is actually fairly stable, and so is cyclobutane. Okay, so the 3-membered ring, the cyclopropane, you define a plane by having 3 points, and so none of those hydrogens can become non-planar because it takes, or none of the carbons can become non-planar because it takes 3 carbons to make a plane. Okay. Now the other thing that I notice about these from the discussion today, if you're watching this on Wednesday, yesterday if you're watching this on Thursday, 2 days ago if you're watching it on Friday morning, is the idea that this puckering also lets these hydrogens then sort of begin to become not as eclipsed as they would be if the ring was perfectly flat. And that actually plays a huge role in cyclohexane. Okay. So we do get this non-planar ring with 4 and 5-membered carbons. So then we have to ask ourselves, so cyclohexane would be the most stable of all of the cycloalkanes. At least that's what the slide said earlier, and I don't think I intentionally tried to deceive you, which is what we would normally call lying. Why is the cyclohexane ring the most stable of all of these? If I apply my logic that I just did, I'd say, well, if all those carbons are in the same plane, I got a 120 degree bond angle. Now I'm stretching the bond angle out. Instead of it being 109.5, I'm now pushing it to 120. Shouldn't I be less stable? And the answer is, well, I should if all 6 carbons are in the plane. but they're not. Cyclohexane puckers even more. And what happens is that we have 4 carbons that are in the plane, and then we bring 1 carbon above the plane and 1 carbon below the plane. And so this allows for, as you can see in this picture, perfect 109.5 degree bond angles. Not only that, but we'll talk about for the Friday lecture, we'll talk about the fact that in cyclohexane, if I looked at this hydrogen, and this hydrogen, if I was to look down this carbon-carbon bond and draw a Newman projection, I'm going to see that these groups are perfectly staggered. So by puckering this ring, the cyclohexane makes perfect 109.5 degree bond angles, but it also avoids any of the hydrogens eclipsing each other. And so this is the most stable of the rings, and we're going to find out for Wednesday's lecture, or for Friday's lecture, that this is actually called the chair conformation of cyclohexane, and it's the one that's the most stable. Now notice for all of the rings that there are positions above the ring and there are positions below the ring. So we're going to have cis-trans isomerism possible for all of these cycloalkane rings. So what we'll do for Friday's lecture is we'll talk about cyclohexane conformations and then begin to rank those conformations in energy, sort of like what we did on Monday, talking about the Newman projections and the conformations of the acyclic alkanes. Okay, so you want to take a look at your book, the sections, the reading sections in particular. Take a look at the ring strain because I touched on it a little bit, and then after you're done watching this and looking at the book, then you can do your online quiz, and then we will talk about this on Friday.